Welcome, everybody, to our July Akka.net community stand-up. I'm joined here by Gregorius here on the Petabridge team.
Hello.
Gregorius, how are you doing today?
Oh, pretty good. And how are you?
It's always busy around here, and we haven't put out as many YouTube videos and blog posts and stuff recently, but we have been. Well, actually, I put one up this week, which we'll talk about briefly. But yeah, we've had a lot of stuff actually going on while I've been here. So let's go ahead and talk a little bit about some of our recent Akka.net releases. So I guess starting with Akka.net 1.525. Yeah, this was my bad. This whole release here. So we had a small problem that we introduced in Akka.net 1.521 through 1.524, which is that the log filtering feature that we introduced to make it easier to turn on like more verbose levels of logging, but also exclude logs from some internal Akka.net sources that you may not be interested in, or even your own application sources if you want. That log filtering feature has been, hotly demanded by some of our production users that are running big Akka.net clusters and that type of thing. Well, small problem with the way I implemented it. And it was a really small, really stupid bug, but it's a pretty major, like breaking feature, which is that if I go and open up the original issue here, Akka.net 1.521 truncated log source timestamps and log level from all the messages. So instead of a log message looking like this, it ended up looking like this. And I happened to notice this when I was working on Turbo MQTT. And yeah, that's a little bit of a problem. So Akka.net 1.521, 22, 23, and 24 were all affected by this. That's why we've marked those packages as having critical bugs on NuGet. So that got fixed in 1.525. And we've added basically a regression test to make sure that the log format can't change without us knowing in the future. So we have a really similar, we use Verify. So Simon Kropp's Verify library for this. We use Verify for our API surface area right now to go ahead and make sure that our API can't sneak in breaking changes by accident. So we are also now doing that exact same thing for our log format too, just so this type of issue can't sneak by us again. We also fixed a couple of other more obscure issues, i.e., this really strange one with scheduled messages resulting in serialization errors when you're working with a router that's remotely deployed. That's like an edge case of an edge case of an edge case, but we fixed that because a user ran into it. So we took care of that. And we've also been doing a lot of work on Akka.Discovery, which is going to come up over and over again. Which brings us to our next release that we've done, the current stable release of Akka.net 1.526. Gregorius, why don't you go ahead and talk a little bit about not just 1.526, but also, well, I guess we have this kind of baked into our future section, so maybe we'll save it then, but save it for that part. But basically, you're kind of laying the groundwork for this project we're going to be discussing towards the end of our upcoming releases section today, right?
Yep.
Yeah. So basically, we've been doing some prep work to make it so you can use Akka.Discovery. This is our service discovery system for bootstrapping clusters, etc. We've been doing some legwork to make it possible to use Akka.Discovery to populate the initial contacts list for ClusterClient. We've got one user in particular that's trying to do this across several fairly large Akka.net clusters. And that's forced us to go ahead and kind of harden the design of Akka.Discovery and Akka.Cluster Tools.ClusterClient as well. So we've been kind of working in tandem on the Akka.Discovery implementations and on ClusterClient. And we've been doing new releases that kind of add support for things like being able to run multiple instances of your Akka.Discovery system concurrently in the same process. I keep using the royal we here, but it's really Gregorius doing all that work. One other thing we did is I made some improvements in 1.526 to improve traceability support for timing messages in Phobos. If you're not familiar with Phobos, Phobos is our commercial product that adds open telemetry support to Akka.net. Most of what Phobos does is it basically helps ensure that instrumentation just works out of the box, and it also does things like trace propagation. It's also very good at being able to control noise, and it's fairly performant. Phobos is been the subject of a lot of performance engineering work over the past year. Now, one thing that we added in 2.54 is by default, Phobos will not trace scheduled messages. These tend to be super noisy, so we do not want to trace them by default. So that's one thing we don't do. However, it is useful to actually measure how frequently things are happening on a timer driven schedule. And what we had before we shipped Phobos 2.54, what we had prior to that was basically you would just see this giant blob of like I scheduled tell message, and that could represent dozens of different message types potentially. For most user defined code, those messages probably weren't all that interesting in the first place. So that's why we haven't really had a lot of end users bring that up before. But one of the things we'll get into in our show and tell presentation today is we've actually been building out over the past month a test laboratory for being able to do lots of quality assurance work on Akka.net. And a lot of what that involves is actually using Phobos to measure system activity. When I say system activity, I mean the actors that are built into Akka.net. So in this case, we're looking at things like we did a lot of experimentation with Akka.Management in order to chase down a socket leak issue there. We did a lot of work on cluster sharding to try to track down a really nasty issue. Gregorius, you've done a bunch of work on ClusterClient and on Akka.Discovery and on the health check system, all using the test lab.
Mhm.
So we've been kind of improving the quality of tracing and metrics for our own internal QA work. Is one thing that's changed over the past month or so. So that's why this release is out now. We're going to have another release of Phobos coming out soon that allows you to trace actor shutdowns in a way that you can't really do right now. It's been possible for a while to trace actor starts and actor restarts. We track that pretty efficiently. But actor terminations outright has not been something we've really tried to measure using tracing. Some of the problems that we've been investigating with our test lab require us to track actor terminations much more aggressively than we're used to. So we are now in the process of adding tracing support to Phobos for that as well. So that's another thing to keep an eye out on. Um, Gregorius, do you want to talk us through this MongoDB release? This ended up being a lot more significant than we thought.
Yeah. It turns out that there was a bug in current event by tag query that it never actually stops. So yeah, that we did a fix there, and that was it. Improves our test pass rate from 18% to now 60%, and it should go up to like 80 and 90. So
Yeah,
that
we
one
averaged
bug
some more runs in.
yeah, that bug actually is a pretty nasty bug.
Yeah. So basically that query type, current event by tag, was just straight up broken before it's fixed. We also have everything running on the newest version of Akka.net now. So you're getting the latest versions of reactive streams and all the other stuff we talked about for CVE fixes last month. That's all now resolved, all of it.
Mhm.
All right, good work, Gregorius. This is going to be a great segue into talking a bit about the test lab. But we've made a whole bunch of fixes to Akka.Management this month as well.
Mhm.
Gregorius, do you want to talk a little bit about? We've got this port exhaustion issue. Maybe I can reference this during our show and tell presentation. But do you want to talk
Mhm.
a bit about what you've been cooking inside Akka.Management so far this month?
Uh, yeah, we actually implemented all of the multi-convig feature that you can actually run multiple discovery plugins in parallel now inside your system. It's been added to everything like Kubernetes, Azure, even config at AWS. So you can actually use those to build your own discovery system if you want to. But the thing that we use it for is the ClusterClient discovery that we'll talk about later.
Yeah. So, in order for if you want to bootstrap a cluster using Akka.Cluster Bootstrap, which is one of the components that's built into the Akka management libraries, you always needed to have a discovery engine to make that work. Well, if you want to have a discovery engine for that and one for like being able to advertise which locations in the cluster have a cluster client receptionist, if you're using the cluster client library, Now you can do that. So that requires running 2 different configurations of Akka.Discovery in parallel. That actually was not as easy to do from a configuration standpoint before. So Gregorius has made that possible and has shipped all the components that have that built into it now. So that's all well and good. We'll touch on this issue because this also got fixed in the latest version of Akka.Management port exhaustion problem. We'll circle back on that and cover it during our show and tell today. Okay. So that kind of does it for all the releases we've done so far. And we have a bunch of stuff in the pipeline that we're working on. Future Akka plans. I guess the first thing I should talk about, we actually just had a discussion issue get opened a few hours ago on this bug. We've had a known bug since I guess I opened an issue on it on October. That basically there's a remote chance that you can end up with a shard that appears in 2 different places in the cluster at the same time. Now, I don't know why this is assigned to the wrong milestone, so I'll fix that real quick. This is one of those bugs that we did a lot of investigative work on it earlier this year. Weren't able to find as much, so we sat down and waited for data. We got a bunch more from one of our support customers a few weeks ago, and we've been using the test lab very aggressively to try to reproduce this. So far, we've been able to eliminate a bunch of causes, but we haven't been able to definitively determine what the issue is. The one thing that all the users who are affected by this bug appear to have in common is it looks like it's the D data sort of state mode. All of them are running with that. Any of the ones running with persistence, we haven't had any reports yet that basically there's duplicate shards that can occur there. So this is a pretty severe bug. This is what's getting most of my full-time attention right now. Gregorius is working on some of the other projects related to Akka.Management, MongoDB, that type of thing. This has kind of been my focal point. We think basically what's causing this is that there is a rebalancing operation that gets started by a coordinator on one node. The coordinator moves before it has a chance to fully sync information about that handoff that's already underway. And then a new coordinator starts up. It doesn't have access to that replicated data, basically never had a chance to make it out the door. That's what we think is happening. And the new replicator, when it spins back up, notices the shards are out of balance and rebalances it again. So you end up with what looks like 2 different instances of the same shard. So that's kind of our working theory. I'm going to talk a bit about how we're using the test lab to investigate this. This is kind of my personal front burner issue right now. But since this has been getting some attention from me, I've been mentioning it in chat. We had a user mention it in the on the GitHub discussions page. I figured it was worth drawing some attention to this. We know this is an important bug. Actually, I should probably switch this to confirm bug as well, since I know for sure this is the customer that we've been working with on this handed me a smoking gun. So we know for sure this is real. So I'm going to go ahead and continue chasing this down. That's one issue that we're working on. Another issue, Gregorius, actually, I think you owe me a review on this pull request.
Oh, yeah, I'll do
Yeah,
that.
we have
This is
significantly
my spot.
improved the performance of Akka.Cluster gossip serialization. Long and the short of it, generally speaking, with Akka.NET serialization, it is far faster to, let me scroll down to like our most recent numbers here. Let's see. There we go. It is very unusual for us to take longer to serialize something than to deserialize something. Deserialization is normally the slower of the 2 processes because it involves essentially parsing all of the bitwise objects from its constituent parts and turning it back into a C# object typically. So that's normally always slower. So a good example, serializing a heartbeat versus deserializing it. Serializing it is like 40% faster than deserializing it. That's pretty much normal. The read side is usually the slower operation out of the 2 in most Akka.NET. So imagine my surprise when I see something that's almost perfectly inverted, where the serialization operation takes significantly longer than the deserialization one. This is stinky. This is code smell when you see this. So it turns out the reason why this is as slow as it was is that we had a whole bunch of old code, the code that's been there since 2016, 17, that basically is doing lots of successive iteration and collection materialization off of the same constituent set of objects. And so I was able to inline the creation of a lot of that stuff. And so we went from having a serialization take basically about 8 microseconds down to, if I go down to the very bottom, this is on a different computer, so ignore that. It now takes about 5.7 microseconds. We saved about 40% on 30 to 40% on time. We also were able to reduce memory usage by about half a kilobit on that. The amount of time it'll take to serialize these gossip envelopes grows linearly with the size of the cluster. It was actually growing at a rate of like n squared before. Now it should be big O of n. So we actually improved that a little bit. The reason why you don't see a dramatic improvement here is because we're working with a small data set. This is only a 3-node cluster we're serializing data for. If this was a 300-node cluster, the results would be much more dramatic. So that's something that you have to look forward to in 1.527. And then finally, Gregorius, why don't you talk a little bit about Akka.Discovery support for ClusterClient?
Yes. So ClusterClient was part of Akka Cluster.Tools, and it was old. Like the idea behind it is that you're going to use it on a static network where all of the other node addresses is. So it would be easy just to populate just like a seed node, basically, because everything's going to be static. Nowadays, with Kubernetes, Docker, containers, and cloud, etc., addresses really are static. They're dynamic. So um, the problem we're facing is that once a known address is down, like if it's taken down, then when it's spun back up, it might not have the same address as it is before. So over time, ClusterClient would fail because it wouldn't be able to find its contact points anymore. So what we're doing right now is that we're coupling ClusterClient with Discovery. We've made ClusterClient Discovery just like how it is with Cluster Bootstrap, so that in the event that all of the initial contacts are gone, that they can't be contacted anymore, uh, we would leverage Discovery to find new contact points instead.
Yeah, that's exactly right. It's basically the whole reason we kind of really went down the road of like getting Akka.Management kind of beefed up for Akka.NET 1.5, a couple years ago, and all that. It's just kind of acknowledging the reality of how Akka.NET gets deployed in production environments now. Like Gregorius said, a lot more things rely on virtualized dynamic net software, network address translated addresses essentially. And so you kind of need a little bit more dynamism in how your network works. Now with environments like Kubernetes, it's still possible to kind of have like a static DNS scheme sitting on top of dynamic infrastructure. That's kind of what the service topology gives you there. But that's kind of not how a lot of applications are deployed. A lot of them are deployed on cloud platform as a service options and stuff like that. So we wanted to make it so ClusterClient could work similarly to how Akka.Cluster itself performs using a dynamic sort of discovery engine. All right. So we'll have a little quick short show and tell today. We're going to talk a little bit about the Akka.NET Test Lab. So now, one thing I do kind of want to mention real briefly is that the stuff I'm going to show you in our test lab is basically not public at all. It's all part of our sort of private tail scale network, and the repositories that we're using to run our reproduction experiments, those were also private, mostly because it makes it a lot easier for us to talk securely to our tail scale network when we don't have to worry about pull requests coming in from anonymous people on the internet somewhere. So let me go ahead and actually kind of show what we're up to here. So this is a project I kind of did when our office manager was away on vacation for a week. So I had the office to myself. I went ahead and bought some hardware, a couple of Raspberry Pi units, and one the System 76 really high-end x64 unit. You can see all three of them here. These are my two Raspberry Pis. This is my System 76 unit. I'm going to order two more of these actually because they're working pretty well. And we went ahead and we instrumented a whole bunch. This is basically like a home lab, but running in our office. We've, been a cloud native company for a long time. SDK bin and all of our other sort of like projects all typically run and, platform as a service environments on Azure somewhere. And in the case of SDK bin, we actually use Kubernetes, AKS for all that. But one of the things I don't really particularly care for is that in the event that we need to be able to run software experiments under continuous observation, like some of this cluster sharding bug I'm investigating, for instance, in the event that we need to run this stuff under with full instrumentation, with open telemetry metrics and traces and logs all available, and maybe I need to run multiple permutations of our experiments side by side in order to basically isolate variables, you kind of want to have a fixed cost model for doing that, meaning that you're better off getting a fairly cheap hardware footprint that you can just reuse over and over again rather than trying to get a big dynamic cloud environment. And it kind of depends a bit on how your company is situated. If you have ops people who can just provision VMs and do all that stuff for you on the cloud somewhere, maybe that's a different story. We're a relatively small software company, so what I figured would be the kind of the better option would be just buying some relatively cheap hardware. I think I spent between the router, the Raspberry Pi units, the external storage, and our System 76 unit. This was maybe slightly under $2,500 to get all this stuff set up, which is that's about 6 weeks worth of what our AKS cluster on Azure costs, to put that in perspective. And we run this continuously at much higher levels of traffic and also with much more powerful CPUs and greater core counts overall than what the AKS cluster does. So what I basically have here, I'm probably not going to pull up our Notion document where I have all the different URLs exposed, but what we've kind of got going on in our test lab is we have this fully instrumented Kubernetes environment. In fact, let me pull up my client. So I'm SSH'd into one of our machines right now. I was running our performance benchmarks on that. This is our nice x64 machine. I also can use kube control, get all. And whoops, I think I need to do get namespace. There we go. And I can see here that I've got one of my experiments. Duplicate shards control has been running for just about 4 days now. This is using Tailscale, which I'll pull up their website real quick. This is using Tailscale to go ahead and connect everything together. It's about as easy as you can get when it comes to basically facilitating like a corporate VPN. Both Gregorius and I have the ability to log in using our corporate identity provider. So we, Active Directory or Google or any other sort of single sign-on mechanism that Tailscale supports. We can just log in and we get DNS information propagated to all of our local clients, whether it's my computer here at work, my iPhone can connect to it, and a bunch of other devices we have, such as like my test laptop that I use when I'm traveling. All of them have the ability to remote into this network and just work. Now, the infrastructure itself isn't all that interesting. We've got a full complement of telemetry services here. So we're using the Open Telemetry Exporter to go ahead and basically aggregate metrics, traces, and logs. I have a Seek instance that we're using to go ahead and do all of our searching. So this is just me looking at a trace for one of our experiments here. I have a whole bunch of little Grafana dashboards that we use that are connected to Prometheus data. So for instance, I have this is the default Phobos dashboard, which I've customized it actually a little bit in order to work with the data format that the Open Telemetry Exporter is using. But I can see here that my duplicate detector cluster has 13 nodes. I can go ahead and see the total number of actors has remained. Actually, sorry, this is just my dupe detector namespace. Let me switch to shard host. There we go. I kind of see we have a relatively even distribution of actors. And if I scroll all the way down, this is because my shard and entity distributions, which I can see here, basically pretty much even. We can't get it perfectly even because there might be an odd number of nodes. In fact, odd number of nodes, odd number of shards, but we're pretty close to it. I can go ahead and keep track of all the entity starts and stops that are happening. These are just entity actors being passivated after going idle. I can keep track of my message volumes. So over the past 6 hours, we've done, let's see, 73 million remote messages inside this cluster. and a whole bunch of other system messages that we're keeping track of, heartbeats, all this jazz. Here's my actual workload of messages I'm sending. So these are the real application defined messages. So we've done just about 41 million of these out the gate. And that's over the span of about 6 hours. So this is kind of our telemetry setup. And the real business value that we're trying to build with our test lab, the having the full telemetry instrumentation with Phobos and with some other custom metrics is nice. But the real value that we have is if I go to here, this is our actual test. So we have a couple of repositories that are designed to continuously deploy into the test lab. Here we go. I'm trying to make this window a little bigger. Got it. We have a couple of different experiments that all deploy into the test lab, and we have some shared infrastructure. This is all brand new. This didn't exist during our last community stand-up. This is all new code. So we have 4 different flavors of experiments that we've been actively working on over the past month. We have cluster sharding, our duplicate shards experiment here. We have Akka Persistence Azure and our health check here for all this stuff. These are all issues we've been looking into for customers. We have our ClusterClient Akka.Discovery stuff. And then the one I kind of want to look at, because we've completely resolved this issue now, is we had a couple of customers report right around the same time port exhaustion and socket leak issues coming from basically Akka.Management. So what we have here, if I go ahead and make this code sample a little bigger, we have pretty standardized configuration. It uses Akka hosting for everything. We have this a standard method for adding experiment telemetry. And then we have the ability to go ahead and configure our experiment actor system. This will parse some of those configuration options and do things like specify, our Phobos settings, like what do we want to trace, what do we want to measure. It'll also help configure Akka.Cluster Bootstrap and help make sure the cluster forms correctly. That's kind of all the stuff that we got baked into it. And we have the ability to add some experiment-specific actors in here. So, for instance, we have some utility actors that do things like measure how long it takes a cluster to form. And then we also have some custom open telemetry instrumentation, like this one right here, that we use to kind of measure. This is like the C# equivalent of invoking netstat inside our application. This basically lets us know about the total number of open TCP connections and the number of TCP listeners, which if I go back to this issue here, the bug that users were reporting to us was basically that we had, this user, we had one customer that was trying to go ahead and deploy like a 12 or an 18 node cluster all running on one Windows VM. This was in like a staging environment, and they were running into port exhaustion problems. And so we started investigating that issue and trying to get to the bottom of what could be causing that. We had another user that reported a problem with Akka Cluster Bootstrap as well, using too many resources. So we had kind of 2 different data points that suggested that there might be a problem with this module. So what I did is I used the test lab and used that test lab experiment, and we decided to go ahead and use open telemetry to measure how different configurations for Akka.Management might influence the number of open connections. This is the idea of prove your argument with data, right? So one thing we did was I went ahead and measured, okay, looks like for some reason GitHub won't let me pull up full-size versions of these images, which is odd. If I copy image address and paste it in there, will that work? I guess not. GitHub must be doing this to prevent hot linking of images or something. So I don't know quite what that's about. But the basic idea here, and I apologize for the small size. I was expecting us to be able to zoom in on this. Maybe I could do it this way. Yeah, there we go. We're going to go ahead and, this will be like my grandma trying to go and browse GitHub. I'll just zoom in real far. That didn't really help, actually, but whatever. I'm doing the best I can. When we have, let's say, a 20 node cluster that forms, we end up with an average of about 20 to 23 connections per node, which makes sense. Every node needs to have at least 19 connections for a mesh network for Akka.Cluster. Plus, we probably also have at least one TCP connection open for exporting all of our open telemetry data. And then maybe a couple of other miscellaneous connections for things like health checks and that sort of stuff. However, we noticed that if the cluster was not able to form, and the way we did that was we're using Kubernetes basically to kind of run these experiments. We went ahead and we ran an experiment where instead of like the minimum contact point number that we needed to form a cluster was set to 20, but we only deployed 18 nodes. This meant a cluster could never form. Well, we observed that every single pod had in the ballpark of like 1,100 connections open at any given time. That would explain port exhaustion on, let's say, a 12 or an 18 node cluster. That meant you would have, if you go ahead and multiply, let's say 12 by 1,100, you'd be using a third of all of the available ports on that connection range there. Windows key brings up Zoom. That's a good idea. Thank you, Jimmy Bird. Let me go ahead and give that a shot. Go ahead and use the Boomer Zoomer. All right. So yeah, you can see there about 1,100 or so active connections at any given time. All right, let me go ahead and get rid of the magnifier real quick. So one of the things that we tested is, okay, is the problem here how aggressively Akka.Management is trying to reconnect when we aren't able to form a cluster? So one of the things we did was we scaled up our 18 node sample. We went ahead and we scaled it to its full 20 node complement, which is when we knew, that it would form a cluster. And okay, this isn't working for me. Uh, as you can see here, what happens is we go from like 6 or 1,100 sort of open connections and drop back down really quickly to basically being back to like 20-ish connections again. So we could tell that the number of connections was correlated to basically how aggressively the system was trying to connect. Once all of the HTTP probing that Akka.Cluster Management, Akka.Cluster Bootstrap does, once all that probing is over and the cluster's formed, the number of open TCP connections shot way down. So the test lab kind of helped expose all of this. So then this is the really cool part. It's not enough just to have like an open telemetry environment that, is instrumented. What's really cool is being able to run and deploy multiple versions of your experiment simultaneously with like one variable under test. And in this case, the variable that we decided to test was the polling interval. How frequently does Akka.Management poll to see if a node that we discovered via Akka.Discovery is actually available? We suspected that's what was driving the growth in TCP connections. So the 1 second interval, which is the default, this is like our control for the experiment, that was generating 1,100 connections per node. If we bump the interval to 5 seconds, that value dropped to 260 to 280 connections. And then if we raise it all the way up to 10 seconds, that value dropped to 100 to 105 connections per node. Bear in mind, this is for, an 18 to 20 node cluster. So we knew then that the key driver of that connectivity growth was that polling interval. So we could just go ahead and call it a day and bump the polling interval up to 5 seconds, which is what we ended up doing, by the way, and let that be that. But that wasn't quite thorough enough for Gregorius and I. So what we decided to do from there was use a bit of open telemetry to go ahead and measure how long does it take to form a cluster at these higher times if all the other variables held constant. If all we do is we boost this interval from 1 second to 5, how does that affect cluster formation time? And so here's what we saw. When we went ahead and kept it at 1 second, the default, it took basically, and by the way, this is a range. So these are all the different pods individually, all, let's say 21 of them. It took somewhere from 50 to 5 seconds to go ahead and either join or form a cluster. And that's really dependent on how quickly Kubernetes spins up each of these pods. Because when you deploy a stateful set with, let's say, 22 nodes in it, Kubernetes might, is going to go ahead and allocate 1 pod, then 2 pods, et cetera. And if we need to wait until there's 20 pods available in order to form a cluster, those oldest pods are going to have a much longer cluster formation time than the youngest pods are. That's why you can see a distribution like this in the data. Well, if I change the value to, let's say, 5 seconds, we end up with basically non-convergence, where the value just keeps going up and up and up and up. And what this exposed was that boosting that value, basically of setting that probing interval to 5 seconds, could result in a condition where the cluster never actually formed correctly. And as it turns out, this was the result of a really simple timeout bug, right, Gregorius?
Yes, it was. We didn't quite calculate the timeout correctly.
Yeah, and it was basically, if correct me if I'm wrong, it was basically that the timeout was independent of the polling interval, so it didn't like slide.
Hmm.
They didn't slide together. In other words, right?
Yep. Yep.
Yeah. So we fixed that, and then I don't think I have the chart on here, but we retested it, and basically what we found was that the cluster formation time was relatively similar at 5 seconds and at 1 second, because the real thing that kind of determined how long it took the cluster to form, it had a lot more to do with how quickly Kubernetes provisioned stuff than it did with like the actual machinations of Akka.Management itself. So we were able to, so we could determine at that point it was safe for us just to go ahead and increase that default interval. That would give us a, essentially it would tax the TCP and port system a lot less heavily than it did before, without really impacting Akka clusters formation time all that much. That was the conclusion that we ended up coming to as a result of this experiment. So what's really interesting about the test lab work that we're doing is it's basically the combination of having a bunch of shovel ready reproduction samples that we can just fire up. If there's ever an issue in the future with people wanting to know how long does it take Akka management to form a cluster, or how heavy is it on the network, or if we have any sharding issues that we need to investigate, or issues with Akka.Cluster tools, we have ready-made samples we can just deploy directly into a Kubernetes cluster without having to write any code. It all uses a standard configuration and standard telemetry. And we have a whole bunch of baked in receivers for that already running in the environment it's getting deployed into. So all of that work can get amortized over many successive projects in the future. That's one really big advantage. But the other one is that we're doing all this automation. In this case, the automated stuff that you saw was really like the measurement on things like cluster formation time and socket growth and all that, which allows us to kind of run multiple permutations of these experiments automatically, like behind the scenes. So, like, Gregorius and I can go do something else and then check in on how our experiments are going and see, well, looks like there's some sort of bug that's preventing Akka.Cluster from forming. Or it looks like, with all these different versions of this experiment we're running, we're not getting convergence on any of them, which tells us that our theory might be wrong on why this behavior happens the way that it does. And we need to go and revisit that and probably design a new experiment in order to accommodate it. So the reason why we're kind of showing this is mostly to just kind of share with the community some of the approaches that we're taking to quality assurance in order to try to tackle performance issues, some of these distributed system bugs, and also the introduction of new features. These are all things that we're trying to kind of do in order to make our QA process not take as long, make it more robust, and also, probably the most important thing, make it automated, make it so we can kind of run a lot of this stuff behind the scenes. We're a small team. It takes a really long time to ramp up an Akka engineer. So it's not that easy for us to go ahead and, let's say, scale our staff that way. So the more leverage we can get out of good automations and good visibility in using tools like Phobos and really good environments for being able to run lots of things in parallel, more power to us for being able to do that. So that's it for this month's community stand-up. Thank you all very much for spending a little bit of your Wednesday watching us. We appreciate it. And if you have any questions or comments, please go ahead and reach out to us in Discord. We're always happy to take your questions. Otherwise, don't forget to like and subscribe. Thank you very much.